Hi, in this video I'm looking at this problem here where a 15-meter long ladder rests against a vertical wall. The base of the ladder is sliding away from the wall at a rate of 0.3 meters per second, and we want to know how fast the top of the ladder moving down the wall when the bottom of the ladder is 8 meters from the base of the wall. So let's draw a diagram of what's going on here. So if we have our wall, and we have our floor, and we have our 15-meter long ladder, we know that the base of this is moving away at 0.3 meters per second. And we want to know how fast the top is moving downwards. That's the speed we want. Now, if we set up our walls as axes, so I have the x-axis and the y-axis, that means I can set up my rate here as the change in x over time, and my rate here as the change in y over time. And it also gives me the ability to say that this distance here to there is x, and the distance of the ladder moving down is y. And so that means I can actually go to Pythagoras' theorem and say that our x squared plus our y squared equals 15 squared. And this enables me to set up a rule that relates what's happening to the top of the ladder and the bottom of my ladder, because that's what Pythagoras' theorem does. So now to get the rates, I'm going to derive this equation with respect to time. So I'm going to have d dt of x squared plus d dt of y squared, and that's going to equal d dt of 15 squared. And so I'm going to have a look at each of these derivatives one at a time. So d dt of x squared we can't normally do because I'm trying to derive with respect to time and I don't have time. I've got x, but I can use the chain rule and use some implicit differentiation to work out what I need to do. So we're going to have d dt of x squared, and I want to write a derivative here that I can do, which is going to be, well, I'm trying to derive x squared, which has x in it, so I want the derivative with respect to x, and I need to cancel out that dx, so I'm going to put the dx up here. And d dx of x squared is 2x, and I'm left with dx dt, and so that's what we're going to have when we go back to our derivative down here. If I look at d dt of y squared, we can do the same. I'm going to have d dy of y squared times dy dt, and I can do d dy of y squared because it's going to be 2y, and I'm going to be left with dy dt. And so now, if I substitute into my differential here, I'm going to have d dt of x squared, we have worked out as 2x dx dt, plus d dt of y squared, we have worked out to be 2y dy dt, and d dt of 15 squared, constants derived down to 0. So I'm after in my question how fast the top of the ladder is moving, and that's dy dt, that's what we're trying to work out. So I'm going to rearrange this to isolate dy dt. So we've got this 2x dx dt, which is added on, so we can subtract it off both sides. So I'm going to have 2y dy dt is going to equal negative 2x dx dt. And then I'm going to divide both sides by this 2y, so that way we have dy dt is going to be negative 2x divided by 2y multiplied by dx dt. Those 2's are going to cancel out, so that's going to leave us with negative x over y, and dx dt we know is 0.3 because dx dt was given us. It's the rate of change of the movement of the ladder away from the base of the wall, so we've got 0.3. And so we are left with dy dt of negative 0.3x over y. So that's our rule for the rate of change of the height based on the movement away from the wall here. And so now I just need to look at what happens when we are at x equals 8. So when x equals 8, which is what we want, when the bottom of the ladder is 8 meters from the wall, how fast is the top moving? Well, when x equals 8, we would substitute 8 into this rule for x, but I need to know a y. So that means I need to go back to my quadratic equation, x squared plus y squared equals 15 squared, and substitute x equals 8 into this. So we've got 8 squared plus y squared equals 15 squared. So y squared is 15 squared minus 8 squared. And so y is going to be the square root of 15 squared minus 8 squared. And getting that as an answer is 12.69. And so we can now substitute into our derivative dy dt is going to be negative 0.3 times by 8 divided by 12.69. So dy dt is going to be negative 0.189 meters per second. So when the base of the ladder is 8 meters from the base of the wall, the top of the ladder is moving downwards, indicated by a negative of 0.189 meters per second. And so we are done. So if we have a problem where we've got possibly two rates, which we do, we had the rate of the movement of the bottom of the wall and the rate of the movement of the top of the wall, and they're related through some rule, in this case Pythagoras' theorem, we can work it out by writing in our rule, deriving it using our implicit differentiation in this case, or we might just need a chain rule, and that gives us a rule for that derivative we can substitute in and get our answer.